So just like we did with tangent, we can use the sine and cosine ratios to help us find lengths. So again, we can remember our definitions with our acronym SOHCAHTOA. And in this case, it says determine the length of PQ to the nearest tenth of a centimeter. So if I'm looking at PQ, that's the line segment from P to Q. It is opposite the vertex R, so I could label it with a little r. And I want to find little r. Now, based on the angle that I have, so the angle that I have is the 67 degrees. First thing I might do is I might label that the 10.4 is my hypotenuse, because whatever's opposite your 90-degree angle is always your hypotenuse. The one that I want to find, little r, based on the 67 degrees, is that my opposite side or my adjacent side? Opposite. So based on the 67 degrees, r is my opposite. Going to my definitions, if I know the hypotenuse, I'm either going to use sine or cosine. I want to use my opposite, so it tells me I should use my sine ratio. So we start by writing out our definition. Definition of sine: sine of 67 degrees equals opposite over hypotenuse. And again, your calculator has that ratio memorized. Whenever you have a 67-degree angle, the opposites divided by the hypotenuse is always the same. And so if I want to find out what r is, I'd use my algebra and say I want to get r by itself. Well, I'm dividing by 10.4, so I'm going to multiply both sides by 10.4. I'll take out my calculator. 10.4 times sine of 67 degrees to the nearest tenth, 9.6 centimeters. And a little bit of a time to appreciate what your calculator has done for you. Because having the calculator know that special relationship, having trigonometry realize that that relationship was 67 degrees, if we type just sine of 67 degrees into our calculator, it's apparently 0.92, which means that the opposite side is 92% of the hypotenuse. And the fact that it has that memorized, we can just, in a simple calculation, say, I know that this other length has to be 9.6 centimeters. Before trigonometry, if I gave you the same question, you would have to draw this triangle out with a protractor at 67 degrees, measure 10.4 centimeters accurately, measure your 90 degree accurately, and then take out your ruler and measure from Q to P. Okay? And I guarantee you, you won't get 9.6, you might get 9.5, maybe 9.7. Your measurements are going to cause you to have some sort of error, just human error in the measurement. And now trigonometry not only allows us to do it much faster, I don't know how fast you're with a protractor and drawing triangles, okay? But it allows us to figure out that opposite side really quickly. And so it is really quite powerful, the fact that your calculator has all of those ratios, and mathematicians have figured out all of those ratios that we can use. Okay, I'm going to give, well, let's do this one together. So we want to find JK, which is little m. I'm going to label this, that side's my hypotenuse. I know the angle 65. If I put all my definitions up on top, okay, with 65, the 7.6 is the opposite. So I know it's going to be either sine or tangent that I need to use. Which one do I want to find? I want to find the hypotenuse. So it's telling me I need to use my sine ratio again. That's not to say that the other ratios won't solve for things, but the sine ratio will find it the quickest. So writing out my definition of sine, if I do sine of 65 degrees, it is the opposite side, which is 7.6, divided by the hypotenuse, which is little m. Compared to our first example, this one's a little bit more complicated because the variable that we don't know is in the denominator. So we have to take an extra step and multiply both sides by m. That will simplify on the right, and now we'll get m times sine of 65 degrees equals 7.6. And now we can divide both sides by sine of 65 degrees because it's multiplying. The opposite of multiplying is dividing. And we get m by itself. And this is something that we can type into our calculator. If you have the fraction button, by going alpha y equals, I'd use that on your calculator, because then you can type it in exactly as you see it. Sine 7.6 on top, sine of 65 degrees on the bottom, and we get 8.4 to the nearest tenth. One thing I always do with my calculations after I do them, I take a quick scan of my question. I should actually tell you all the things that, I'm not going to tell you all the things that go on inside my head because there'd be like way too much. But when I finish a math question, okay, 8.4, one of the things I did is I said, my hypotenuse should be the longest. Is 8.4 bigger than 7.6? Because if it isn't, it's telling me I've made some sort of mistake somewhere. So I do that as a check. I reread the question again as soon as I finished. I reread it so that I could find out what kind of rounding do I need. Is there a part B to the question? Sometimes you solve one part of a question, then you read a question, and I actually don't like those questions that ask you 18 things in one question. It's like, oh, to keep going back and keep solving more and more stuff. They should. Most math exams now try to avoid that by having like part A, then part B, then part C. And once you get to your IB exam in grade 12, they even have some that go up to like part I. They're that long. The biggest question I've seen on an IB exam was one question out of 24 marks. And it went all the way up to like part H, and like part E had part EI, part EII. It was just massive in one question. And I imagine, what if they decided not to break that up and just have that as like a half-page paragraph at the beginning of your question? Please do all the following. Would not be very nice. So I read over the question again. Another thing that you maybe didn't realize because I was doing it in my head, every time I do my work, a couple of things for doing your work that makes you make a few less careless mistakes. For one, when you look at my work, do you see that in between my work, I've got a little bit of a space there? Something, because if you use every line in your notes, or if you tighten everything together, your brain might later on not go, where did one step end and the next step begin? So having a little space in between is helpful. Another thing that we're going to start to model a lot in our questions this year is we do our math work vertically. So every time I'm done this step, I go to the next step, I can just look above and say, does it match up? Does it logically make sense how I went from that one to the next one? Okay, and I've shown my work with the green. Oh, I multiplied by m, and that's how the m came up over here. And then I divided by sine 65. Okay, that's how m got by itself. And then from here to here, I guess it only makes sense that I must have used my calculator, because I don't see how mental math I could have gone from this to this otherwise. Okay? And it's in checking over things that you might go, oh, maybe I approximated here at the end. Maybe I should add that detail because I forgot to do that. From a radar station, the angle of elevation of an approaching airplane is 32.5 degrees. The horizontal distance between the plane and the radar station is 35.6 kilometers. How far is the plane from the radar station to the nearest tenth of a kilometer? So on this question, the first thing I would notice is I don't have a diagram given to me in the question. I just read through the whole question, and a diagram would really help. So at the end of reading through the whole thing, now I've got to figure out what I'm going to draw and get an idea for the picture first. I've got an angle of elevation of 32.5 degrees, a horizontal distance, an airplane coming in, landing, and a radar station. And so draw my airplane, draw my radar station. And we're wanting to find out the distance between that airplane and the radar station. Drawing a right angle triangle with the ground, we're told that the angle of elevation, an angle of elevation is going out from a horizontal line looking up, so that this angle here is our 32.5 degrees. We're told that the horizontal distance is 35.6 kilometers. So off to the side, if I write out my three definitions, and I say, I want to find this. So I'm going to use the letter x for something I don't know. I haven't labeled my vertices, so I can do that for whatever value it is. And I want to find the hypotenuse. And based on the 32.5 degrees, so maybe I label that this is always our hypotenuse. The 35.6, will that be adjacent or opposite the angle that I'm getting? It's adjacent. So when looking at the values that I have, because I know the adjacent side, I'm either going to use cosine or tangent. I want to find the hypotenuse, so I have to use cosine. So I write out my definition for cosine. Cosine of 32.5 degrees is my adjacent side, 35.6 over my hypotenuse. At this point, x is in the denominator, so we have to multiply both sides by x first. And that would, on this side, simplify my x's away. And now that x is in my numerator or on the top, I can get x by itself by dividing both sides by cos of 32.5 degrees.
Nina Beauregard, please report back to class, please. Nina Beauregard, please report back to class.
Ooh, I'm going to get my approximation signs all ready. (35.6) divided by cos of 32.5. 42.2. Going up to read my question, nearest tenth of a kilometer reminds me that I need to put kilometers in there. I do a quick check. I was solving for the hypotenuse. Did it come out to be the longest side? Yes. Hey, there's something interesting here. If we do all the angles added up, all the angles in a right angle triangle add up to 180, that means if this one's 90, I often just use, what do these two have to add up to? Those two angles have to add up to 90 as well, because 90 plus 90 is 180. I'm going to get you to estimate this side. Okay? We know that this side is 35.6. This side is 42.2. Could this side that's left be bigger than 42.2? No, because the hypotenuse has to be the biggest. Can it be less than 0? No. So now we know it has to be somewhere between 0 and 42.2. My question for you, do you think it should be bigger than the 35.6 or smaller than the 35.6? And why do you think it's going to be smaller? Because of the way I drew my triangle? I'm going to give you a warning. Sometimes I do not draw my triangles to scale. I just draw a triangle. So it could be that this is just poorly drawn. How do we know it should be smaller than 35.6? What do you think? Well, you could solve it, right? You could do a squared plus b squared equals c squared and actually get it. Just guesstimating, because I can do 35.6 squared in my head, right? Okay, so we could estimate using that. Okay, but I think that those numbers are a little bit, sometimes can be a little bit big, especially in this case.
The angle on the 32.5 is pretty low.
The angle on the 32.5 is pretty low. Watch, imagine I'm holding a triangle in my hands. And you just imagine the length from fingertips to fingertips. As I make that angle smaller, what happens to that opposite side? It gets smaller and smaller and smaller. And what will always happen on a triangle is the side opposite the bigger angle will be a bigger side. That's why hypotenuse, 90 degrees, can you see it? 90 degrees is always our biggest angle. That's why your hypotenuse is always the longest. But then your next biggest angle here is the 67.5, so opposite of that will be a bigger side than opposite the 32.5. Yes, Claire? Yeah, it would be 57.5. Is that bothering anybody else?
What?
Thank you, thank you, thank you. It has to add up to 90, and it added up to 100. But 57.5 is still bigger than 32.5, and that still makes that opposite side the largest one. So I'm going to give you some time to practice some of this stuff in class, so take out your textbooks.